Hello, welcome to our webinar. My name is Stephanie Reese, and I am the Engineered Wood Specialist at APA in our Market Access and Development Division. I will serve as the moderator for this session. Today, we'll be diving into the ANSI APA PRG 320 standard for performance-rated cross-laminated timber, or CLT. We'll cover what the standard includes, its applications, and how it impacts design and quality assurance in construction. Before we start today's webinar, I need to cover some housekeeping details. This presentation will last about an hour. Slide handouts are available in your control panel. All participants are muted to ensure clear audio. And if you have any questions, please submit them via the questions pane. Some of them will be answered in the chat and others during our Q&A session as time permits. A recording will be available on our website at www.apawood.org in about a week for review or for you to share with others. APA has represented the engineered wood industry since 1933. Originally, we were the Douglas Fir Plywood Association, and about 30 years ago, in the early 90s, we became APA, the Engineered Wood Association, to reflect the broader product scope. We're a nonprofit trade association representing manufacturers of structural engineered wood products. We support product testing, research, and quality assurance, while educating industry professionals on the proper product use. While product testing and member mill certification is an important part of APA, we have a dedicated field team to assist you. Our engineered wood specialists are located throughout the U.S. and Canada, and their contact information and territories are available on our website. There's going to be a lot of information covered today, but all the documents are available for free download at our website. I'd also like to note that today's webinar is approved for both AIA and ICC continuing education credits. So about an hour after the conclusion of the webinar, an email will be sent to you, and then it will include a link that you can get customized certificates of completion. The information provided in this webinar is based on APA's research and field experience, but no warranties expressed or implied are made. APA and its members are not liable for any damages resulting from the use of this information. The user should consult local regulations or a design professional to ensure compliance with relevant codes and standards. APA does not control the workmanship, quality, or usage conditions, so it cannot guarantee product performance or design outcomes. Contents copyrighted, reproduction, or use for AI training requires written permission from APA. Your feedback is important to us, so you'll see a QR code here on your screen. Point your smartphone to it now, and it will take you to a link you can complete at your convenience. We'll also show it at the end of the presentation. But this time, I want to introduce you to our presenters for today. Patrick Schleisman, an engineered wood specialist for APA based in Atlanta, and Lindsay Custer, an engineered wood specialist based in San Diego area. In their roles, Pat and Lindsay work with designers, builders, code officials to provide construction and design guidance for the use of APA members' engineered wood products. Pat has spent more than 30 years in the wood products industry. After earning a civil engineering degree from Iowa State University, he started his career in project and construction management before going on to earn both his PE license and an MBA. He later joined Georgia Pacific, where he represented their plywood mills and engineered lumber business. His background is a unique blend of product expertise and business development, making him more of a solutions and strategy guy. Lindsay's a registered professional engineer in California with more than 7 years of structural engineering experience, earning her master's degree in structural engineering from UC San Diego and her bachelor's in architectural engineering from Cal Poly. Lindsay supports the Southwestern region, helping designer builders and code officials as well, specifying and the use of engineered wood products effectively and optimally. She also has a special focus on sustainable design. For those of you who are just joining us, welcome to our webinar titled 4 Things to Know About North American Mass Timber Standards. I'll now turn the program over to our first speaker, Pat.
Thank you, Stephanie, and thank you to everyone for joining us today. Stephanie, Lindsay, and I have turned off our cameras to better facilitate our presentation. APA members produce a wide variety of engineered wood products, including plywood, oriented strand board, glued laminated timber, cross-laminated timber, wood eye joists, and structural composite engineered lumber. Since 1933, the list of APA members has expanded. We have 177 member mills spread out across 23 states and 7 provinces. You can find this list in our manufacturer directory page on our website, apawood.org. Forgive the small print. On the website, you can also find lists of our member manufacturers specific to selected engineered wood products. Please feel free to reach out to me with any questions about navigating our website. In no specific order, here's a list of our member Glulam manufacturers and our member CLT manufacturers as of November 2025. Almost all of them make Glulam as well. We don't favor any member of the APA, so our website will randomize the order of the company names. Here are the APA-affiliated CLT manufacturers on a map. Note the regional locations. You can visualize coast-to-coast coverage and service for your projects. Today we'll learn about engineered wood products, especially mass timber, and how and why mass timber has been incorporated into projects across North America. This webinar will explore glue-laminated timber and cross-laminated timber, covering manufacturing processes, design specifications, performance, and environmental benefits through real-world case studies. We will also cover the North American CLT standard and its implications for design professionals. CLT that meets PRG 320 standards is code recognized, assuring its quality and mitigating risks for owners, designers, and builders. I want to summarize the learning objectives for today's course. To understand the scope and requirements of the North American CLT standard, PRG 320, and to learn more about glue-laminated timber and its North American standard, A190.1. Finally, we want to identify the structural and architectural benefits of building with mass timber. For today's presentation, after setting up with some background information, we're going to start by defining mass timber and its place in the engineered wood family. Then do an overview of glue-laminated timber and cross-laminated timber, go into an overview of CLT and the building codes, and do a deep dive into the PRG 320 standard, and end with some mass timber case studies that you can reference. So, what is mass timber? But before defining mass timber, let's begin by defining engineered wood, which is the type of mass timber we are involved with at APA. Engineered wood is a range of derivative wood products which are manufactured by binding or fixing the strands, particles, fibers, veneers, or boards of wood together mechanically or with adhesives. In simpler terms, it's taking pieces of wood and putting them back together in a strategic way. So, what are actual engineered wood products? Generally, EWP can be divided into two categories: panel products and framing products. This slide lists the most common types of panel products. We talk a lot about wood structural panels because that's the terminology used in the code. Plywood and OSB are both wood structural panels. Over the years, EWP panel products have expanded to include siding and more specialized products as well. Framing products are used for a variety of applications. In general, eye joists are typically used as floor joists and roof rafters. Glue-laminated timber or glulam are typically used as beams and columns. A group of other engineered wood products are classified as structural composite lumber or SCL. Cross-laminated timber can be considered in both framing and panel categories. CLT is made from sawn lumber pieces stacked on top of each other. The orientation of the wood grain changes throughout the depth. Just like plywood or OSB, CLT panels have a strong axis span direction. Engineered wood products that bear the APA trademark are manufactured in accordance with APA or national standards. The trademark is the manufacturer's assurance that the product conforms to standards noted on that trademark. APA members commit to a rigorous program of quality inspection and testing. Many engineered wood products are proprietary and use proprietary engineering standard reports and APA product reports for their code recognition, product use, and design information. Competition might drive a manufacturer's recipe. Admittedly, we don't have time to do a deep dive regarding this point. Note that Glulam and CLT can be proprietary, more so for Glulam than CLT. We also have many additional resources available for free download on our website. Website links for each reference throughout the presentation will be shared later. Let's take some time and look at the newest kid on the block, mass timber. Mass timber is getting a lot of attention wherever we go. Developers, designers, code officials want to know more about mass timber. Woodworks reports that as of September of this year, there was almost 2,600 mass timber projects that have been constructed or were in design in all 50 states. The major benefits of mass timber construction are that it's a warm, aesthetically pleasing, environmentally responsible means of construction that can be used in multifamily, multi-story, in both commercial and single-family applications, that allows for faster, efficient installation and better carbon sequestration than cold-formed steel or concrete construction. Notably, the Ascent building in Milwaukee, completed in 2022, stands as the world's tallest mass timber structure at 25 stories. Looking ahead, the Edison, a 32-story mass timber high-rise, also in Milwaukee, is set to become the tallest of its kind in the U.S. when completed. Construction just started in June. Mass timber is a broad term that addresses construction that utilizes products that come in many forms, which does include cross-laminated timber, but also includes other newer products, as well as Glulam beams. You can also include Glulam decking and traditional post and beam framing. Other mass timber products include nail-laminated timber and dowel-laminated timber that are designed in accordance with the American Wood Council's National Design and Specification for Wood Construction. There's also mass plywood panels and veneer-laminated timber. Today, we'll be focusing specifically on traditional CLT and Glulam used in mass timber construction. Glulam uses layers of 2x lumber that are bonded together in a flat stack. The wood grain runs parallel to the length of the beam, which is common with all the engineered beam products. It is commonly used for headers, beams, studs, and columns. Glulam is an engineered wood product composed of 2 or more laminations of dimension lumber glued together. The laminations are glued with end finger joints to make lengths of any size that the manufacturing plant can handle. The long lengths are glued together in layers or plies to the desired beam depth for the intended end use of the product. Things like knots, knot holes, and grain characteristics are dispersed throughout the layup, which maximizes the strength of the Glulam. Glulam are available in a variety of I-joist compatible depths. Widths to match framing are available. As with the other engineered wood products, they are readily available in lengths up to 48 feet. There are also many other sizes, and one of the coolest things, custom shapes, are available on special order. Glulam beams do not have the same strength properties throughout the depth of the member. Manufacturers place the best material where it is needed most to get the most strength out of the beam. Economics plays a part in the construction of the beam. If we consider a balanced layup, the beam has equal capacity in both positive and negative bending, and is primarily used in continuous beams or long cantilevers. Looking at the layup of an unbalanced beam, they have unequal capacity in positive and negative bending, and are primarily for use in simple beams or short cantilevers. Because of this unequal capacity, unbalanced beams have a top and a bottom and must be installed correctly. In response to high stiffness that was being produced by some SCL manufacturers, Glulam manufacturers developed a high-strength Glulam beam that married traditional solid-sawn plies with high-strength LVL located in the outer plies, giving us the best of both the Glulam and LVL worlds. Hybrid beams use LVL top and bottom laminations to increase the tensile strength. Although not available as stock items, they come in conventional Glulam depths as well as in I-joist compatible depths to fit well with today's engineered wood floor systems. U.S. produced Glulam is manufactured to ANSI standard A190.1. Covered are things like lumber material requirements, laminating and adhesive requirements, assembly for the face, end and finger joining, and the final dimension of the beam. The standard, as well as building code, specifies that a third-party grading agency must be involved in auditing the manufacturing process. Note that Canadian Glulam is governed by different standards and shall be trademarked with CSA for commodity products or CCMC for proprietary products, plus an APA logo if an APA member. Here's an example of a Glulam trademark. Please refer to our E30 construction guide for guidance on preparing Glulam specifications. If you're considering using imported Glulam products, it's important to evaluate all its characteristics closely. Products manufactured outside of North America may not meet the stringent standards of A190.1 relating to adhesive, heat durability, fire performance, quality assurance, and third-party certification. Accepting Glulam products without demonstrated conformance to A190.1, as required by the U.S. Building Code, carries the responsibility of structural engineering and fire safety design, as well as acceptance of product quality and durability in structural and fire performance. See APA Form W500 for more information. Glulam beams are available in different appearance classifications as noted in APA's technical note, Glulam Appearance Classification for Construction Applications. Bottom line, structural properties for a given Glulam layup are independent of appearance consideration. Premium is identical to framing regarding strength characteristics. Form Y110 goes on to discuss appearance subclassifications that include LVL in the outer laminations. For example, industrial-L appearance and framing-L appearance classification. Here are example photos of industrial, architectural, and premium appearance classifications. I won't cover the details here, but you can visually see a difference. Along with a range of appearance classifications, Glulam can be produced in curved shapes to meet end-use requirements. The natural colors are a function of wood species and finishing. Glulam beams are also available in lengths greater than 100 feet. Here we see a beam in the top right photo that measures 10 3/4 inches by 72 inches with a 115-foot clear span that is installed at the Oceans exhibit at the Indianapolis Zoo. Glulams typically come in widths ranging from 2.5 inches to 10 3/4 inches, but that doesn't prevent manufacturing something wider. Here's an example of a 21-inch wide by 27-inch deep by 110-foot long Glulam column. You can see in the photo there that there are multiple plies in each layer in the makeup of this member. In addition of the multiple plies per layer, we can also see where a conduit was run through the length of the member. This member served as the trunk of a palm tree cell tower. Now let's discuss the product that probably is most synonymous with mass timber construction, cross-laminated timber, or CLT for short. CLT is a versatile product that in many ways can be considered a wide beam or a panel with strength in two directions, where they can be used as a structural member for floors, roofs, and walls. It's a large-scale prefabricated solid engineered wood panel. CLT consists of several layers of kiln-dried lumber boards, typically stacked in alternating directions, bonded with structural adhesives and pressed to form a solid, straight, rectangular panel. CLT panels consist of an odd number of layers, usually 3 to 7, and may be sanded or pre-finished before shipping. While at the mill, CLT panels are cut to size, including door and window openings, with state-of-art computer-controlled routers capable of making complex cuts with high precision. Extra fabrication may be possible to accommodate electrical chases and conduits, for example. Finished CLT panels are exceptionally stiff, strong, and stable, handling load transfer on all sides. The panels can be manufactured at custom dimensions, but check with each manufacturer as transportation restrictions might dictate their size, especially their length. CLT is fast and easy to install, generating almost no waste on site thanks to factory prefabrication. CLT also offers design flexibility and low environmental impacts. It can be locally or regionally sourced. For these reasons, cross-laminated timber is proving to be a highly advantageous alternative to conventional materials like concrete, masonry, or steel, especially in multifamily and commercial construction. Typical sizing is between 2 and 10 feet wide, up to 60-foot lengths, and as thick as 20 inches. This is what a typical APA trademark will look like for CLT. It's relatively simple, only listing 4 pieces of important information. 1, the grade qualified in accordance with the standard. 2, the mill number, which indicates where the panel was manufactured for quality tracking and control. 3, the product thickness. And 4, the reference product standard, PRG 320. Now over to Lindsay to cover mass timber code updates, product reports, and PRG 320.
Thanks, Patrick. I'll start with mass timber and building codes. The 2021 International Building Code expanded the types of construction from 9 to 12 by adding 3 new construction types within the Type 4 heavy timber classification. The new types 4A, 4B, and 4C allow mass timber structures up to 18 stories and 270 feet. Each of these Type 4 building classes have different maximum heights and stories, along with different protections and fire rating requirements. The 2024 IBC defines mass timber as structural elements of Type 4 construction, primarily of solid, built-up, panelized, or engineered wood products that meet minimum cross-section dimensions of Type 4 construction. Now let's get into code updates pertaining to the lateral system. The 2021 IBC references the 2021 Special Design Provisions for Wind and Seismic, also commonly referred to as SPIDWIS, which recognizes the use of CLT as a lateral force resisting element. Section 4.5 covers the design of CLT diaphragms, and Section 4.6 covers the design of CLT shear walls. Note that there are no tabulated nominal capacity values in SPIDWIS for CLT diaphragms or shear walls. The capacity of CLT diaphragms are based on the connection capacities used to transfer diaphragm shear, and CLT shear wall design is based on Appendix B, which provides design and detailing requirements. The 2021 IBC also references ASC 716, which predates SPIDWIZ 2021, so CLT shear wall systems are not recognized. ASC 7 2022 is the first ASC to do so, which is referenced in the 2024 IBC. Now we are going to do an overview of ANSI/APA PRG 320, the North American product standard for CLT. PRG 320 is the only bi-county recognized ANSI/APA standard. I just wanted to note here that the latest 2024 IBC reference standard for CLT is PRG 320 2019. However, APA always performs testing, evaluations, and inspection services in accordance with the latest standard per ISO requirements, unless a customer requests in writing to evaluate products to an older standard. So I'll be focusing on PRG 320 2025 as it's the latest version of the standard. We're going to start with some product terminology, so we're all on the same page when talking about CLT. Then we will cover component requirements, panel dimensions and tolerances, performance criteria, quality assurance, and end with design properties of basic CLT layups. A lamination in CLT is a piece of sawn lumber or structural composite lumber, including stress-rated boards, manufactured lumber, or edge-joined or in-joined lumber, which has been prepared and qualified for laminating. We'll get into some of the lamination requirements later in this presentation. Each layer of CLT is made up of an arrangement of laminations laid out parallel to each other in one plane. A longitudinal layer consists of laminations oriented in the major strength direction of the CLT panel, which we will define on the next slide. And a transverse layer consists of laminations oriented in the minor strength direction, also referred to as a cross layer. A layup is an arrangement of layers in a CLT panel determined by the species, grades, number, orientation, and thicknesses of the layers. Just like Glulam, CLT layups can be both balanced and unbalanced. Balanced layups refer to the structural layers in the CLT being symmetrical about the center of the CLT panel thickness. All the basic CLT layups listed in Annex A are balanced. Unbalanced layups are asymmetrical. These are custom layups and require approval by an approved agency. CLT grade refers to a class of CLT determined by the combination of grades of laminations in the longitudinal and transverse layers. Basic CLT grades and layups in PRG 320 are listed in Annex A. The major strength direction is the direction with the greater strength and bending of the CLT panel. This is the direction the longitudinal layers are oriented, and the CLT length is always measured parallel to the major strength direction. In balance layups, the major strength direction is the general direction of the wood fibers and the surface layers of the CLT panel. Wood fibers in any decorative or architectural layer are not considered structural and not an indicator of the major strength direction of the CLT panel. For some unbalanced layups, the major strength direction may be difficult to define or determine without a model calculation. See Appendix X3, Section 3 for guidance on developing an unbalanced CLT model. A joint is defined as an interface between two surfaces, and a bond line is a layer of adhesive between the boards. An edge joint is the narrow face of adjacent laminations in a single CLT layer. Edge joints with adhesive are considered to have an edge bond line, but not all edge joints require adhesive. An end joint is formed by bonding of two pieces of laminations in a CLT layer and is required to be a finger joint or a scarf joint. A face joint is formed by bonding faces of laminations in adjacent layers in a CLT panel. All face joints have a face bond line. Now that we have reviewed some CLT terminology, I'm going to start with the CLT material component requirements, which are the individual laminations and the adhesive used to put those laminations together. There are many lamination requirements in PRG 320, including grade, size, moisture content, face bonding surfaces, and gaps between laminations. Laminations within the same layer shall be the same thickness, type, grade, and species or species combination. Note that this is only true for laminations in the same layer. Laminations in different layers may be different than the layers above or below. Each sawn lumber lamination is to have a minimum published specific gravity of 0.35. For a structural composite lumber lamination, a minimum equivalent specific gravity of 0.35 is also required. In the longitudinal layer, the laminations are to be a minimum visual grade number 2 or a minimum MSR, and in the transverse layer, the laminations are to be a minimum of visual grade number 3. PRG 320 section 6.1.4 lists the size tolerances for CLT laminations, including lamination width in both the longitudinal and transverse layer, and net lamination thickness. As discussed previously, not all edge joints are bonded, so the standard provides size tolerances for the gaps between unbonded adjacent laminations based on whether this gap is in the face layer or inner layers of the CLT. Note when edge joints of laminations are not bonded with an adhesive or not filled in with filler, small air gaps are common per CLT. These gaps will affect the air tightness throughout the CLT thickness, and the effect will depend on the number of CLT layers and actual gap size as manufactured. If air tightness is an important requirement, such as in fire containment, thermal resistance, or sound attenuation, additional measures should be incorporated in the assembly design, such as the use of an airtight membrane like a concrete floor topping or finished gypsum wallboard. The standard also discussed face bonding and moisture content requirements for the laminations. Additionally, there's requirements for the lamination joints, including end, edge, and face joints. We aren't going to get into the specifics today, but those details are in PRG 320, section 6.3. The next CLT component we will discuss is adhesives. Like the Glulam standard, PRG 320 requires elevated temperature performance evaluation of adhesives used in CLT. The intent of this evaluation is to identify and exclude the use of adhesives that permit CLT char layer falloff, which would result in fire regrowth during the cooling phase of a fully developed fire. If you are considering using imported CLT products, it's important to evaluate all characteristics closely. Products manufactured outside of North America may not meet these stringent standards of PRG 320 relating to adhesive heat durability, moisture durability, and overall fire performance. accepting CLT products without demonstrating conformance to PRG 320 as required by the US and Canadian building codes carries the responsibility of the structural engineering and fire safety design, as well as the acceptance of product quality and durability and structural and fire performance. See APA Form S500 for more information. Now that we've covered component requirements, we can move on to requirements for the CLT panel as a whole. The standard covers dimensional tolerances for the length, width, and thickness of the panel as shown graphically. Textured or other face or edge finishes are permitted to alterate the tolerances specified. The designer will be required to account for any loss in cross-section or specified strength due to those alterations. The manufacturer may be contacted for recommendations if this is something being considered in design. There are also squareness and straightness tolerances. For squareness, unless specified otherwise, the length of the two panel face diagonals measured between panel corners shall not differ more than 1/8 of an inch. And for straightness, unless specified otherwise, deviation of the edges from a straight line between adjacent panel corners shall not exceed 1/6 of an inch. All these tolerances are to be measured at the time of manufacturing. I have mentioned basic CLT layups a few times, but I want to get further into the different requirements of a basic versus a custom layup. Basic CLT grades and layups are those provided in Annex A of PRG 320. They are balanced layups, meaning they are symmetrical about the neutral axis, and they consist of alternating layers of the same lamination thickness. Custom CLT grades and layups are all layups not provided in Annex A. They may be unbalanced, contain different lamination thicknesses, and have adjacent layers oriented in the same direction. However, they are not required to have any of these characteristics. APA members publish their custom CLT grades and layups in their APA product report. APA Technical Services provides 3 types of product reports for the manufacturers of mass timber, including ICC/APA joint reports. In all these product reports, the code compliance pathway is well spelled out and the design values are provided. Now I'm going to touch on some of the mechanical property testing in PRG 320. Flatwise bending is bending of CLT under transverse loads applied to the panel face, creating out-of-plane bending and flatwise shear, also known as planar or rolling shear. Along with flatwise bending, there is testing for flatwise shear stiffness, and I'm going to group this kind of testing into the overarching category of flatwise mechanical properties, which are required qualifications for structural performance. For basic CLT layups and grades, this testing is done to confirm the design values shown in Table A2 of Annex A. For unbalanced CLT layups, the current standard now requires a qualification test to be conducted on both positive and negative flatwise bending moment capacity. Edgewise bending is bending of CLT under loads applied to the panel edge, creating in-plane bending and edgewise shear, also known as in-plane shear or shear through the thickness. Along with edgewise bending, there is testing for edgewise shear stiffness, and I'm going to group this kind of testing into the overarching category of edgewise mechanical properties, which are optional qualification tests. It's logical to think these properties would be required for CLT used as part of the lateral system. However, for wall and diaphragm design, base material strength rarely controls. What can control is the deflection or drift requirements, and in those cases, the manufacturer would need to conduct an edgewise shear stiffness test. Section 9 of PRG 320 defines how quality assurance must be maintained for CLT after a product has been qualified. The purpose is to ensure that CLT continues to meet performance expectations and that any change in manufacturing or materials that could affect performance is detected early. Manufacturers are required to have a documented in-plant quality assurance system. This system outlines sampling methods, testing frequency, and record keeping. All quality assurance records must be available for audits, and production lots are held until test results confirm compliance. For APA members, an APA auditor would be performing these in-process checks. Daily testing focuses on the integrity of end, face, and edge joints. These tests check bond strength, wood failure, and durability, with samples taken evenly throughout each production shift. Effective bond area is also checked, assuring that bonding surfaces maintain at least an 80% effective bond area. Lumber quality and glue application are closely controlled to prevent issues like excess warping or glue skips that could weaken the bond. For ongoing verification, special procedures are outlined for face and end joints. And finally, all finalized panels undergo visual and dimensional inspections for size accuracy, shape, and squareness as discussed previously. Minor variations are allowed, but only if they don't compromise the product's structural or performance requirements. Now let's get into Annex A, which provides design properties based on CLT grades and layups. When looking in the annex, the CLT grades are denoted using letters and numbers. E stands for Machine Stress Rated Lumber, or MSR lumber. This CLT grade has low variability in strength and stiffness. V stands for Visual Grade Lumber, meaning a trained lumber grader assesses grades based on appearance and characteristics, just like the ones you're probably familiar with in the NDS. And S stands for Structural Composite Lumber. This slide shows Table A1 located in Annex A of the PRG 320 standard. This table provides lamination design values for the basic CLT grades. Note the E, V, and S notations in the CLT grade that we discussed previously. Like Glulam, the number that follows indicates a certain layup of the product. The first page of Annex A gives the composition description of each layer shown in this table, including the wood species and grades of the laminations used in both the longitudinal and transverse layers. This slide shows Table A2 located in Annex A. The table provides the design properties for basic CLT grades and layups using the lamination design values we just looked at in Table A1. Generally, this would be the table used for the structural design of CLT. As you would expect, the thicker the CLT panel and/or the better the grade of its laminations, the more strength and rigidity the CLT panel will have, meaning longer spans and higher load carrying capacities. Similar tables are also provided for design used in Canada. Let's do a quick, simplistic design example to show how the table can be used. Let's say I'm designing a CLT floor slab either through hand calculation or modeling, and I calculate that I have a demand of 7,500 pound-feet per foot in the major strength direction and 1,200 pound-feet per foot in the minor strength direction. The next step would be to go into the NDS, Table 10.3.1, to calculate the adjustment factors that would be used to convert the reference bending moment capacity, FBS effective, seen in Table A2, into the adjusted bending moment capacity, FB as effective prime, which is required to be equal or greater than the demand calculated. For bending, the adjustment factors are the load duration factor, C sub D, the wet service factor, C sub M, the temperature factor, C sub T, and the beam stability factor, C sub L. For this example, I'm using the low combination dead plus live, so my C sub D is equal to 1. And let's say all other adjustment factors are also equal to 1.0, so the reference moment capacity equals the adjusted moment capacity. However, this is not always the case, so do not forget to check the adjustment factors. From here, I can go into the table and see, based on bending capacity, there are two panels here that would efficiently meet the demand. The difference between these two panels is E2 is made of Douglas fir larch machine stress rated lumber, and E5 is made of hem fir machine stress rated lumber. I also wanted to note that we are only seeing part of table A2 on the screen, so there are other CLT grades in Annex A that might be a good option for our design. Beyond Annex A, there are a number of additional sections at the end of the standard I wanted to quickly touch on. Annex B introduces the compartment fire test, which is a rigorous 4-hour simulation that verifies adhesives in CLT remain structurally sound under an applied load and full fire exposure. The adhesive must prevent char layer falloff, also known as delamination, which would result in fire regrowth during the cooling phase of a fully developed fire. Appendix X2 gives the test setup used in the development of Annex B. Appendix X1 outlines two CLT appearance grades, architectural and industrial, so that designers and fabricators align expectations about visible wood's appearance. Appendix X3 dives deeper into the engineering modeling used to develop the design values in Annex A. It explains how the design, stiffness, and strength values in the table are derived using mathematical models and how cross-lamination layers interact. Finally, Appendix X4 captures the history of the standard itself from early development through the latest 2025 update. We wanted to finish today's webinar by sharing some APA case studies that utilize mass timber. As Patrick mentioned earlier, APA has a wealth of publications available on our website. I'm going to quickly touch on some of the case studies APA has done that highlight CLT and Glulam and demonstrate the wide variety of project types where mass timber has been utilized. Form W170, Engineered Wood Gets an A, is a publication featuring multiple case studies of different K-12 schools that have utilized engineered wood, including mass timber. These schools featured CLT, glulams, LSLs, LVLs, and plywood, and note the benefits associated with the use of those products. Form A115 shows how glulams can be used to create unique architecture. In the Beaverton City Library, a forest of glulam trees stands tall. Symbolically connecting the library structure with the surrounding city, the glulam trees are characteristics of Beaverton, whose slogan is "The City of Trees." The case study for First Tech Federal Credit Union highlights the building's use of CLT and glulam and the small erection crew that is typical with CLT. CLT and glulam were used in this office building in Kelowna, British Columbia. This case study shows how designers can get creative with their Glulam connections. Form S-120 features a case study for Portland's One North development, a mixed-use project featuring Glulam beams and columns. Aesthetics always play a part with exposed wood, and this project really demonstrates this. Here's a project I've been lucky enough to see in person, Cathedral of Christ the Light in Oakland, California. This project features an exposed glulam space frame structure designed to survive a 1,000-year earthquake. The building utilizes a combination of glass, wood, and steel. Form J140, the case study for this project, is really worth the read. This publication, Form V130, features multiple projects and discusses locally sourced wood, lower costs, shortened construction times, and the environmental benefits from using CLT and Glulam. I'll conclude with a case study for the Brailsford WSU Visitor Center. Wood from mountain pine beetle infested trees was used here, which I think is very cool. Other features include quick installation, lower costs, and just highlighting wood's natural beauty.
All right. Thank you, Lindsay, for highlighting these great examples of cross-laminated timber in various types of places. And Pat, thank you as well. So we have a few minutes for questions. And here's that QR code again to the survey. We'd really appreciate you completing that. So let's get to some questions. I'll start with Pat for the first one that we received. Is North American produced CLT as competitive with European imported CLT?
Yes. On projects bid a few years ago, U.S. producers were still working things out, including fabrication capabilities. I like to think now they've turned the corner and can be quite competitive, not to mention tariffs. No question that the European importers have the luxury of low-cost timber in comparison. The bulk of their price is for transportation to the U.S., frankly. Keep in mind that the U.S. CLT can be locally or regionally sourced, manufactured, and transported to the job sites.
All right, thank you. Next question, I'll ask Lindsay. How does regional wood fiber affect the CLT grade?
Yeah, good question. CLT is available in multiple grades and species throughout North America, and you can see what species are used in the basic CLT layups in Annex A. A designer should consider specifying wood species that are regionally available from the closest manufacturers to both cut down on shipping costs and for the environmental impacts. Manufacturers in Canada and the Northwest primarily use Douglas fir. So, for example, one could specify an E2 or a V1 grade CLT in those regions. And manufacturers in the Southeast primarily use spruce pine fir or southern yellow pine. So one could specify an E4 or V3 grade CLT in the Southeast. I would recommend reaching out to manufacturers in your region for more information on what's regionally available.
And thank you. Next one, I'll ask Pat this one as a product expert. But what do you feel the main barriers are to a broader use of CLT, like in commercial construction?
That's a great question. CLT might not replace stick framing in single family or even in multifamily construction, although CLT is being used in panelized moderate income apartments at a reduced cost. Mass timber construction can be competitive in the traditional steel and reinforced concrete structures scenarios. As previously discussed, building heights can be achieved up to 18 stories or 270 feet, but many local jurisdictions haven't got there yet. Frankly, not all specifiers are yet familiar with CLT design, detailing, or erection methods. Lots of upfront coordination is required. Early coordination between structural, architectural, and MEPs is required. As the new kid on the block, durability perceptions remain, and time will prove that out. Until proven, there could also be insurance and financing barriers as well. I'll stop there.
Okay, thank you. And we have time for one more before we finish up with the few remaining slides. If I didn't get to your question or your question didn't get answered, someone will reach out to you. So rest assured, if you haven't got your question answered here, it will be answered. So Lindsay, how do balanced versus unbalanced layups affect CLT panel performance?
Yeah, that's an interesting question. It's not that easily answered. The function of unbalanced layups for Glulam and CLT is very different, and it's much more complex for CLT. So a balanced versus unbalanced layup for Glulam is mostly driven by structural performance. However, unbalanced layups for CLT is mostly driven by non-structural aspects of the design or production, such as appearance, allowable substitutions, certification strategies, fiber costs, just to name a few. So really it should be discussed on a case-by-case basis.
Okay, thank you. All right, so again, if you have any additional questions that you think of after the webinar, you can reach out to our regional representatives near you, in which I'll direct you on how to reach out to them. But before we go there, here are some links via the QR codes if you're interested in reviewing or downloading those publications that were referenced today. Don't worry, if I move away from the slide, you can view them again from the handouts. You do need to register and sign in to the APA website to download the publications. And as I mentioned, APA has field staff located throughout North America and North America. Your local APA Wood Specialist is a free resource for you, available to assist in questions that you may have regarding engineered wood products. Their individual contact information can be found on the staff contacts page of the APA website. To navigate to this page, you go to apawood.org and select Contact at the top. This will take you to our main contact page. If you select Learn More option under the Market Access and Development, you will navigate to our Engineered Wood Specialist page with a map here, and that shows the different territories where we have field staff. And you scroll down and can select the appropriate region and get contact information for your local engineered wood specialist. And finally, make sure you're signed up to receive our APA newsletter so that you'll be notified of our future webinars and updates to the APA publications and standards. To receive it, all you need to do, starting from the home page again of our website, is to click on the Sign In, which is in the upper right-hand corner of the page. And then in the menu that drops down, simply select Register. And from there, you'll need to let us know what you'd specifically like to receive, which in this case is the APA Update newsletter. Additionally, we have resources to assist you at our help desk, and they can be reached through email at help@apawood.org. You can also complete online form or by phone.